All right, guys, it is really, really early this morning. So hopefully I don't make too many mistakes here. Okay, so hopefully we get to this point in class this week where what we've been working on, where we've said, we're finding the slope of a tangent line at a point, okay, where, x is whatever that value is on the x-axis. Okay, well, this is called the derivative, okay? So you're talking about slope of a tangent line. Okay, and obviously that's how it was originally come up with. Fermat, as well as a whole bunch of other mathematicians were trying to do this. Okay, and that was the very first sort of application of this method, and we call it the derivative. But there was a lot of other applications over the years, and you'll see those applications during class in the weeks to come. Okay, so we call it the derivative. Okay. Now, a lot of times they'll call, rather than saying derivative, they use this notation, this f apostrophe, which we call f prime. Okay, so if the derivative exists, okay, so if f prime exists, okay, we say that f has a derivative at x, or f is differentiable at x. Okay, so the derivative exists, we say that f is differentiable. Okay, now we also have this alternate method. Okay, they will give you the exact same thing. In some instances, this guy is a heck of a lot easier to use than this guy. Okay, now I know you guys are pretty good with this top one. Okay, and so the bottom one's a little new. Okay, and hopefully we get a chance to actually do some of these problems in class this week. I know we're going to get a chance to do some of these. Hopefully it's this week. Okay, if we don't get to it this week, we'll get to it next week. Okay, so I'm going to primarily work with this guy down here today in the videos. The reason being is that obviously we're pretty familiar with this guy. So let's try to get familiar with this guy. And then once we have, gone through both of these, using both of these forms of the derivative or Fermat's method, okay, then it'll just be up to you. I don't care which one you use. Doesn't make any difference to me. Okay, so we have a whole bunch of notation, okay, with this derivative. And the good thing about the textbook you have is Dr. Ferris uses all of it at times. Okay, so when we're talking about the derivative of f of x or the derivative of y, okay, sometimes we just use this prime notation. So we just say y prime or f prime, okay, and we just pronounce it that y prime or f prime. Okay, but that means we're taking the derivative of y or the derivative of x, or I'm sorry, the derivative of f. Okay, you see this a lot. This guy is really helpful in a number of different applications because this guy acts as a fraction. Okay, dy dx. So that's how you would read it, dy dx. Basically what we're saying is we're taking the derivative of y with respect to x, or the derivative of f with respect to x, which is right here. Okay, so we might say df dx. Okay, so this one would kind of like be reserved for function notation if we had f of x equals as opposed to y equals. We say df dx, okay, which is the derivative of f with respect to x, the same exact thing here. Okay, then sometimes they'll use this. We say d dx of f. Okay, so d dx means you're taking the derivative of what? Of f. Okay, so it's just another way of saying this. Okay, so d dx of f. And then the last one is using this capital D with this sort of subscript x. Okay, so that means we're taking the derivative of the function f. Okay, which is the same as this and that. And obviously, if you're not in function notation, it's the same as both of these. So just all these different ways to represent, okay, you're dealing with the derivative. Okay, that's all they are. Okay, so let's see what we can do with this guy. Okay, and I had to do this morning to sort of refresh my memory here. Okay, so we are finding the derivative of g, okay? So I'm going to use dy dx because I'm so used to using that. So I say, okay, well, dy dx, okay, and remember this guy, we're referring to the derivative, okay, of g of x. That's what we're referring to. Okay, so we say the limit as x approaches a, okay, of g of x minus g of a all over x minus a. Okay, and then I've got to deal with this guy right here. Okay, so let's see what we get. We get the limit as x approaches a. G of x would be radical x minus 1 minus g of a would be radical a minus 1 all over x minus a. Okay, so we take a look at that, and obviously if you just go ahead and try to evaluate, this will be 0, and the numerator will be 0 over 2. We'll get 0 over 0, okay, because obviously this radicand would become a minus 1, and so we'd have the square root of a minus 1 minus the square root of a minus 1, so that's 0. And clearly the denominator is 0, okay? So we've got to manipulate this guy, okay, because obviously we don't like this guy, okay? So I've got to manipulate this guy and somehow reduce it and get rid of this x minus a down in the denominator. Okay, so right here, I'm going to use a conjugate, okay? And somebody might be asking, well, why are you using a conjugate? And I would say, because it works, okay? So if I multiply the numerator and denominator by the conjugate, okay, of the numerator, okay, so we have radical x minus 1 minus radical a minus 1 all over x minus a. So remember, conjugates are binomials that are exactly the same other than their sign. So the conjugate of this guy, this binomial up in the numerator, I just change that minus to a plus. Okay, so I multiply by the binomial radical x minus 1 plus radical a minus 1, and I do that above and below. Okay, now when you multiply conjugates, you get a difference of squares. And so we say, okay, well, if I multiply this binomial by that binomial, okay, the o's and i's cancel each other out, so I just get first term squared minus second term squared. Okay, so I would have radical x minus 1 squared minus radical a minus 1 squared. And then down below I have this factor of x minus a times this conjugate, the square root of x minus 1 plus the square root of a minus 1. Okay, so let's see what happens here. Hopefully this works out. Basically, I know it's going to work out, assuming I don't make some kind of mistake. All right, so if we square root, we just get the radicand. So I'd have x minus 1 minus, same thing, square root, we get the radicand. Okay, I have to subtract the quantity of a minus 1. Okay, and then down below I have my x minus a, and I have my binomial square root of x minus 1 plus the square root of a minus 1, like that. Okay, so if I look up here and I distribute that negative 1, notice I'm going to get x minus 1 minus a plus 1. And notice those 1's cancel each other out. So I get the limit as x approaches a. Up above, notice I'm left with just x minus a. And then down below, notice how it's going to cancel with the x minus a. And I'm just going to be left with this conjugate. Okay, so we take a look there and we cancel things off. And so I'm just left with 1 over the square root of x minus 1 plus the square root of a minus 1. Okay, and now that I've got these binomial factors of x minus a to cancel off, and obviously that's what creates a 0, and that's what creates a 0 as x approaches a. So I get them to cancel off, and I say, okay, well, couldn't I just evaluate now? Okay, so let's take a look at what happens. 1 over, well, as x approaches a, x becomes a. So this square root of x minus 1 becomes the square root of a minus 1. Obviously, as x approaches a, it doesn't affect this at all. And notice that these two radicands down below are similar, so I just get 1 over 2 times the square root of a minus 1, whatever a is. Okay, now if you wanted to rationalize that, you could do that by multiplying above and below by the square root of a minus 1. So we would get the square root of a minus 1 all over 2 times the quantity of a minus 1. Okay, so either one works out fine as your answer. I'd probably just stick with that guy. Okay, so you can see algebraically how this method works. Okay, let's try another one. Okay, so this guy does not involve a radical, which usually means it's going to be a little easier to do. Okay, hopefully that's the case. Okay, so let's see what's going on here. Okay, let's get it set up, and then I'll get this sheet out of the way, because if I remember right, I'm gonna need all of this. Okay, so we say dy dx, the derivative, equals the limit as x approaches a of f of x minus f of a all over x minus a. Okay, so we're going to get the limit as x approaches a of f of x is just 2x to the 5th minus f of a would be 2a to the 5th over x minus a. Okay. All right, so we take a look here, and you say, okay, well, I could factor out a 2 up above. Okay, and so what are we going to get? Limit as x approaches a of 2 times x squared minus a squared. I'm sorry, that's not squared, that's to the 5th power. That makes a big difference. Okay, that's x to the 5th minus a to the 5th all over x minus a. Okay, so now notice we're taking the limit as x approaches a. A is some number. So this a squared is a constant. Okay, so this is a difference of 5th powers. Okay, and believe it or not, x minus a would be a factor of x to the 5th minus a to the 5th. Okay, and I can divide that out. All right, so we're going to have to divide this guy out. Okay, and so let's see, I take my x minus a, and I divide that into this difference of 5th powers. Okay, so I have x to the 5th. Now the problem is I don't have any x to the 4th, x cubed, x squared, x, and on down, so I got to add in those terms. It'd be plus 0x to the 4th plus 0x cubed plus 0x squared plus 0x minus this a to the 5th, whatever that constant is. And I have to do my long division, okay? So let's see. X to the 5th divided by x would be x to the 4th. So I get x to the 4th. I multiply through, and so I get x to the 5th minus ax to the 4th. And we subtract. Okay, so 0 minus a negative a, so I get ax to the 4th. Bring down the 0x cubed. And then repeat the process. Ax to the 4th divided by x will be ax cubed. Okay, so ax cubed times x is ax to the 4th. ax cubed times negative a will give me negative a squared x cubed, and then I subtract. Okay, so obviously these go away. 0 minus a negative a squared x cubed would give me positive a squared x cubed. Bring down my 0x squared. Okay, and then a squared x cubed divided by x would be a squared x squared. Okay, and multiplying through, a squared x squared times x would be a squared x cubed. And then a squared x squared times negative a gives me negative a cubed x squared. And subtract, so these go away. 0 minus a negative a cubed x squared would give me positive a cubed x squared. Bring down the 0x. Okay, so I go a cubed x squared divided by x would be a cubed x, like that. Multiply through, a cubed x times x would be a cubed x squared. And a cubed x times negative a gives me negative a to the 4th x. And then again subtract. These guys go away, and so I'd have 0 minus a negative a to the 4th x, so I get positive a to the 4th x, and then bring down by minus a to the 5th. And then we go a to the 4th x divided by x, so it just gives me a to the 4th. And then multiply through, so I'd get a to the 4th x minus a to the 5th, and clearly everything goes away. Okay, so it does divide evenly, which I knew it would. Okay, so we're going to take this guy, bring it down here, and we say, okay, I have the limit as x approaches a, and up above, notice that I divided out an x minus a, and I am left with this long quartic right here. Okay, so I get a to the 4th plus ax cubed. I'm going to need a little bit more room. Okay, plus a squared x squared plus a cubed x plus a to the 4th. Okay, right here. And then don't forget, I almost forgot, don't forget I have that factor of 2 up in the numerator. Okay, and then down below I just have that x minus a. And so notice that the x minus a's cancel. Okay, and so I get the limit as x approaches a. I've got that factor of 2, and then I have this long quartic. A to the 4th plus ax cubed plus a squared x squared plus a cubed x plus a to the 4th. Okay, so once we have these factors of x minus a divided out, now I can just go ahead and evaluate. Okay, so I've got that 2. Okay, so as x approaches a, it doesn't affect this, that's just a to the 4th. As x approaches a, this becomes a right there. So I've got a times a cubed. As x approaches a, this becomes a. So I get a squared times a squared. As x approaches a, that becomes a. So I get a cubed times a. And then obviously as x approaches a, it doesn't affect that at all. And notice how this is going to work out just fine. Okay, so I've got a to the 4th. When I multiply these, I get a to the 4th. When I multiply these, I get a to the 4th. When I multiply these, I get a to the 4th, and then bring that last a to the 4th down. And notice they're all similar. I got 1, 2, 3, 4, 5. So I have 5 a to the 4th. And when I multiply it together, I get 10 a to the 4th. And I found my derivative of x approaches a. Okay, now obviously this long division is, I don't know, kind of a pain in the butt, I'll be honest with you. I just did it. I have an easier time doing the long division because of, there's basically two variables. Even though I know a to the fifth is a constant, I've got x and I've got a, so I have an easier time with long division rather than synthetic division. Okay, and that'll wrap it up for this video.